Today we're going to talk about inverse functions, which you should be thinking we are inverting functions. We are undoing functions when we're talking about inverse functions. As always, feel free to jump to a particular timestamp in this video that you're interested in. As a roadmap for today's lesson, we're first going to be going over what types of functions even have inverses. Those are called one-to-one functions. One-to-one functions are functions where, spoiler alert, it's not only that every x has one y, but each y actually has one x as well. Then we're going to talk about inverse functions. What are inverse functions? How we find inverse functions from a variety of different ways of presenting a function. Then we're going to end on the domain and range of an inverse function, which is really one of the most powerful tools we have with inverse functions, because if on the regular function it's kind of tricky to figure out either the domain or the range, we can utilize the inverse function to help us figure it out. So first of all, what type of functions even have inverses? Well, remember, something is a function if every x has one y, if every input has exactly one output. And it's going to be an inverse function if the other way around works as well, so where every y has exactly one x. So let's check this. So here, if we look at our inputs and we look at our outputs, we have, for example, that 4 maps to 5, 6 maps to 7, 20 maps to 3, and 100 maps to 501, with my inputs being my x's and my y's being their associated, my outputs being their associated y's. And then we want to check this is a function because each x has one y, and it works the other way around, where each y has exactly one x. So this is a one-to-one function because each output has only one input. What about this next one? Go ahead and pause this video and figure out, is this next one a one-to-one function? So if we were to think through if this next one was a one-to-one function, I would recommend mapping out the same way that we just did, where we have the 4 goes to 5, we also have the 6 goes to 5, we have the 20 goes to 5, and we have 100 goes to 501. So even though on this last one, 501 is an output with only one input, 5 is an output that has more than one input. And as soon as you get some output with more than one input, in this case the output of 5 is associated with 4, 6, and 20, it is not one-to-one. And in particular, 5 is an output with more than one input, in this case 3. And as soon as you find one problem child like 5, it is no longer one-to-one. Just like we had a vertical line test to quickly check if each input only has one output, we have a horizontal line test to check if each output only has one input. So to use the horizontal line test, if I have some sort of function, I'm basically going to envision, well, if I have a bunch of horizontal lines, does it cross the function only once? If so, it is one-to-one, and if not, it is not one-to-one, just like it was with the vertical line test. So here, both of these functions definitely pass the vertical line test, because on both of these functions, everywhere I draw vertical lines only crosses once. So they both are functions, but for horizontal line test, one of these guys passes and one of them fails. And I'm going to just delete my vertical lines to make that clear. So which of these is one-to-one and which one is not? This first one is one-to-one because the vertical lines only cross once. Now you might be wondering over here, that was more because I draw my line kind of crooked. If you actually look at the function itself, it's still curving, although not super steeply. And each horizontal line would actually not quite touch the function more than once. We're okay. Only touches the function once. Versus here, this is not one-to-one. One-to-one, because essentially everywhere our horizontal line crosses twice. Or down here, in this case, it's not crossing at all. That's not necessarily a problem. But up here, where it's crossing twice, that's a big problem. That makes it no longer one-to-one. And we care about this because if it is 1-to-1, that means if I were to switch x and y, it would still be a function, which means that if I invert it, if I undo the function, it's still a function. So that's why we care about 1-to-1 functions. So what are inverse functions? So inverse functions, if a normal function takes a x and outputs a y, the inverse function indicated with an whatever the function is, f, g, or whatever, and this little -1 on the top, that takes your y and outputs the x. So this would just be our function over here, and this would be our inverse function. So every time you see this little -1 on your function, keep in mind that's not asking you to raise it to the -1 power, that's asking you to invert it. So let's look at an example where we actually might be dealing with inverse functions. Let's say you only knew the formula to convert Fahrenheit to Celsius, and you want to do the other way around. You're given something in Celsius and you're an American and you're like, by gosh, in America we use Fahrenheit. I want to know the Fahrenheit. So in order to do that, you would have to basically solve for f here. So let's look at that as an example. So the C of f language is saying Celsius as a function of f. So I might even, for my own sanity, just relabel that as C. This f is just telling me the function for Celsius inputs f. Well, I already kind of know that looking at the function. So I'm just going to recall that C. And then I want to solve for f in order to convert to Celsius. So in order to do that, there's a couple different ways that we could do that. As tempting as it is to distribute this 5/9, I actually would argue that it is easier to just get rid of multiplying by 5/9. And how would I undo multiplying by 5/9? I would divide by 5/9. And keep in mind that fraction division I could also think of as multiplying by the reciprocal. There's also the two-step way of doing it, which is what I'm going to actually show, that will result in the same thing as dividing by 5/9, although feel free to just divide by 5/9. First thing I would do is I would undo dividing by 9 by multiplying by 9 on both sides. 9 divided by 9 is 1. I'm left with 9c is equal to 5 times parentheses f minus 32, f being Fahrenheit. Then I would undo multiplying by 5 by dividing by 5s. So then I have 9/5 Celsius equals Fahrenheit minus 32. And then as my last step to solve for Fahrenheit, I would undo subtracting 32 by adding 32 to both sides. Had you distributed, you would have gotten an answer that was still equivalent to this. So I now have a function for Fahrenheit in terms of Celsius that looks like this. So if Celsius in terms of Fahrenheit is 5/9 times parentheses, function Fahrenheit minus 32, the function for Fahrenheit in terms of Celsius is 9/5 times Celsius plus 32. And already you can kind of notice that these are related, because for converting, I'm given Fahrenheit and I want to output Celsius. I first subtract 32, then I multiply by 5/9. That's the order of operations on the Celsius equation. For the Fahrenheit equation, I first multiply by the reciprocal of 5/9, 9/5, and then I add 32. So already these should sort of feel like they're undoing each other. And actually, this is an example of an inverse. So if this is our original, where I input a Fahrenheit and I output a Celsius, my inverse is where I input a Celsius and I output a Fahrenheit, which is something you might have to do at some point. And there's also something really special that's going to happen when I plug in these inverses. So this is asking us to do a composite function. So it's asking us to find C of f, essentially. And the other one is asking us to find f of c. So this is asking us, for this first one, C of f of c being this, is asking us in the Celsius equation to replace everywhere I see its input Fahrenheit with the equation for Fahrenheit. So let's go ahead and try that. So C of f of c and I promise there is a point to this, something very special is going to happen at the end, is 5 over 9 times, and instead of writing Fahrenheit, 9 over 5 Celsius plus 32, and then we still have this minus 32. And now let's go ahead and start to simplify this. So let's tackle any like terms inside the parentheses first. What do you notice are like terms? We have 32 minus 32. And what is 32 minus 32? That is just 0. So then we have 5 over 9 times 9 over 5 times Celsius. Well, 5 over 9 times 9 over 5, even if you don't immediately recognize that will give us 1, let's just kind of naively do this as fraction multiplication. 5 times 9 gets us 45, over 9 times 5 also gets us 45. 45 divided by 45 gives us 1. So when we plugged the inverse into the original, we were just left with the input. Let's try it the other way around as well. So if I were to do it the other way around, if I'm looking for f of c of f, that's saying plug the c of f function in for c everywhere you see it on this outside function f. So let's try that. So that's asking you to plug in the c function is 5 over 9 times f minus 32 into the f function. With this f, I'm actually going to note that with like a lowercase f to emphasize that that's a function we're talking about. We're not talking about the input f. So when we plug this in for Celsius here, then we have 9 over 5 times 5 over 9 times Fahrenheit minus 32, and then we still have this plus 32 on the outside. Now to simplify this, I would just start with this multiplication. Well, 9 over 5 times 5 over 9, that still gets us 1. And if you're thinking about distribution, keep in mind this is actually, you sort of have to distribute the 5 over 9 first, and then you would be distributing the 9 over 5 to that, or you can just kind of think of this as a sequence of multiplication. We have a 9 over 5 times a 5 over 9 times a Fahrenheit minus 32. By the associative property, I am actually allowed to move those particular parentheses. And just say this is really a bunch of multiplication here. And that's that's associative property with multiplication. So 9 over 5 times 5 over 9 becomes 1 times Fahrenheit minus 32 plus 32. Well, multiplying by 1 doesn't do anything. Just keeps everything the same. And negative 32 plus 32 just gives me 0. So I'm again back to that original output. The reason why we did this exercise was to emphasize if I have something that is an inverse, so by definition inverse means I kind of flip-flop those inputs and outputs, and this for the first function I want Celsius and I input Fahrenheit. For the second function I want Fahrenheit and I input Celsius. If I plug them into each other, everything should cancel out but my variable. I should just be left with my plain old input variable there at the end. And that is exactly how you mathematically check that something is an inverse. So here, that's all it's saying in fancier notation, is if you want to check that something is an inverse, algebraically, or another word that may be used is prove something is an inverse algebraically, you prove that if I do function composition with the inverse and the original, with this little -1 on the f indicating the inverse function, then it'll just output my input of, in this case, x. So let's take a look at some examples of that that are more likely to closely resemble how you would see it on an exam or something. So if I want to check if these are inverses of each other, I only have to check one way around. So I need to check if I either plug g of x into f, if that outputs x, or if I plug f into g, that outputs x. While we checked both ways around earlier with the Celsius Fahrenheit example, it's only really necessary to show it for one of these two. So in this case, if I'm sort of thinking ahead, to me it seems easier to plug f into g because I've just got an x down here in the denominator, versus if I plug g into f, Well, it actually might be equally simple because I might notice that the -2 and the 2 might cancel out, but it still seems like something slightly more complicated to plug into the denominator. But you could choose either way. They're both equally valid choices, and if you disagree with my choice, more power to you. You should absolutely disagree with your professors whenever you want, because this is a free country last time I checked. So in this case, I chose to plug f into g, and I was about to write that the other way around. So if I'm plugging f of x into g, that means I'm plugging 1 over x plus 2 everywhere I see an x in the g of x function. So I have 1 over x plus 2, and then I've got this minus 2. And then to simplify this, there's a couple different ways I could go about it. I could just keep in mind that I know dividing by a fraction is the same thing as multiplying by the reciprocal. Or you might have been trained to go ahead and just multiply both the top and the bottom by the least common denominator. That would be another equally valid way to go about this. Where if you do that, then x plus 2 divided by x plus 2 makes 1, and you're just left with x plus 2. Or you could think 1 divided by 1 over x plus 2 is 1 times x plus 2 over 1. And either way, that becomes x plus 2, this whole term. And then you just drop down the minus 2. Then you combine like terms. 2 minus 2 makes 0. And I'm just left with x. If you chose to do it the other way around, I'm going to go ahead and show you that too, because I value diversity of opinion here. You might have thought the other way around was easier. So here I'm plugging g of x into f, the entirety of this. So that means in the f function, I'm going to replace, I'm going to just kind of note, I'm doing a different problem now. In the f function, I'm going to replace everywhere I see an x with the entirety of g of x. That becomes 1 over x minus 2, and then I still have that plus 2. In order to start simplifying down here, I've got a -2 plus 2 makes 0. So then I have 1 over x, and then by either of these same logics, that becomes 1 divided by 1 over x, which is the same thing as 1 times x over 1, which is just x. So either way, I just output x. In order to test this algebraically, it's only actually necessary that you show one or the other on this. You don't necessarily have to show both. Go ahead and pause this video and see if you can check this one algebraically. Here again, you can check it either way. I'm going to choose to plug f into g, but you could have done the other way around. So if I'm plugging f into g, that means I'm finding g of x cubed minus 4, which means everywhere I see an x in g, I'm going to replace it with an x cubed minus 4, and we still have that plus 4. In terms of order of operations, I want to treat this root like a parenthesis, so I want to simplify underneath the root, and -4 plus 4 makes 0. And the cube root of x cubed, just like a square and a square root sort of quote-unquote cancel out, is the same idea here, with the actual logic being, keep in mind, if I took the cube root of 3 cubed, that's the cube root of 27, so you're asking yourself, what times itself 3 times gives me 27? Well, that's just 3. And that's always really going to work out that way, regardless of what I make that. So instead, let's say I took the cube root of, I was about to write down what 2 cubed was, which is 8, but let's say I got it from the original. To cube root of 2 cubed, that is the cube root of 8. The cube root of 8 is just 2. Same idea. So that's why they sort of cancel out. And it cancels out the other way around, that if I asked for the cube root cubed of 3, for example, that would also cancel out to make 3. Same idea. So in this case, that makes x. So we throw out the word cancel out a lot. You kind of want to think about why it actually works. It's because by definition, a cube root says what times itself 3 times gives me that number. And I already told you it was x times itself 3 times that gave you that number. And that's why we're just left with x. And had you checked the other way around, you should have gotten the exact same thing. Oh, and I forgot to actually write on the slides that yes, that means in these both of these cases, they are inverses of each other because we found that we just got x there at the end. Let's check one more. So go ahead and pause your video. Do you find the same thing here? So here again, you can plug either way. So let's say I found f of g of x. So if I plugged g of x into f, that is 1/3 of x all cubed. Only way this would simplify is that that cube kind of distributes to both. So that becomes 1/3 cubed times x cubed, 1/3 cubed being the same thing as 1 cubed over 3 cubed times x cubed, which becomes 1 cubed is 1, 3 cubed is 27 times x cubed, and no matter what, this really does not look like x. There's no way this will turn into x. So this is not, these are not inverses. And the vast majority of functions, if you try to plug them into each other, are not going to be inverses. So of course, just guessing and checking every single time to see, oh, if I plug this function in, do I wind up with an inverse, would be a very silly way of doing these types of problems. Sometimes you're asked this specifically, but we probably want a more generic algebraic method in order to find inverses. And that's what we're going to go over now. So the reason why, first of all, we care about finding inverses is because the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. They sort of flip-flop. Because remember, for inverses, by definition, we are flip-flopping x and y. And actually just literally flip-flopping x and y is how you find the inverse of a lot of functions. So that's always kind of the first step, is if you know xy is the coordinate on the original, then yx is a coordinate on the inverse. So for example, if I just told you that the function consisted nothing of but the points 1, 2, and 2, 3, for example, that would mean your inverse function consisted of nothing but the points 2, 1, and 3, 2. Just literally flip-flopping x and y. And similarly, the domain of that original would have been 1 and 2, and the range would have been 2 and 3. So then on this inverse, the domain is 2 and 3, and the range is 1 and 2. And this is actually a very, very powerful idea. So one of the most basic ways to find inverse is you flip-flop x and y, which means that the equivalent of flip-flopping all the x's and all the y's is flipping the domain and the range. And that might be even the only step that you're required to talk about for a function and its inverse. Because, for example, let's say I told you on one function, f of 2 is 4 and f of 5 is 12. And I mentioned it's 1 to 1, which means it does have an inverse. What are the corresponding input and output values for the inverse function? So on the original, in function notation, they just told you that the points 2, 4 and 5, 12 exist on the function f of x. So what about on the inverse? Go ahead and pause your video and see if you can write those down. That would mean that I would also have the point 4, 2 and 12, 5. And if I were to note that in inverse function notation, that would be the inverse function evaluated at 4 is 2, and the inverse function evaluated at 12 is 5. What if I gave you that the inverse function evaluated at 6 was 2? What would have to be of the original function? Well, so here they gave you that the inverse has the point 6, 2. So that means the original, I must have the point 2, 6. Or in function notation, that would be h evaluated at 2 is 6. And then we can extend that just one step further to talk about the domain and range. So if I say on the original function, the domain is 1, infinity, and I don't yet know the range, and on the inverse function, the domain is negative infinity to negative 2, and I don't yet know the range, how could I figure out the range? Well, the equivalent of flip-flopping all the x's and y's is if all the x's on the original are 1 to infinity, that means all the y's on the inverse are 1 to infinity. And if all the x's on the inverse are negative infinity to negative 2, that means all the y's on the original are negative infinity to negative 2. So I want you to go ahead and pause this video and try this problem yourself. So here, first let's talk about what even the inverse function would be. So here we're going to be, again, there should be a closing bracket here, but this is all the points on the original function. So on the inverse, you're going to flip-flop x and y on all those points. So if negative 7 comma 9 is one of the points, the new point would be 9 comma negative 7. Negative 3 comma negative 7 was the next one, then we'd have negative 7 comma negative 3. And then you keep going, then we'd have 8 comma 5. And then we would have negative 6 comma 8. That is my inverse function. And then we want to know its domain and range. So on the inverse function, what's its domain? Well, we've got the points 9, negative 7, 8, and negative 6. Notice how I use curly braces to indicate we're not like doing all the points in between. It's just literally those 4 x values. And the range would be negative 7, negative 3, 5, and 8. And notice all these elements in the domain were the range of the original. All these elements of the range were the domain of the original. And this connects to how we find the inverse function for any abstract formula. So if you're given the graph or a table or a list of points, you just want to flip-flop x and y individually. If you are given an abstract function, though, you have to algebraically solve for it. So first you want to make sure it's 1-to-1. Usually that's just given to you in the problem, but you want to double check that. Then you want to flip x and y, because that's always the first step when we're talking about inverse functions. Then you want to solve for y, and then you might want to actually use that inverse function notation. So let's do an example of this. So first thing we want to do, what's not listed as a required step, but what I sometimes like to do is just actually note what the original function is in terms of x and y. So an f of x is the same thing as y. And I just kind of orient myself doing that. That's an optional first step. The real first step you have to do is flip x and y, because now we're looking for the inverse. So instead of y, I write an x. Instead of x, I write a y. Then I want to, and let me just, since I'm on the theme of changing colors for each step, let me keep on going. Then you want to solve for y. There's a couple different first steps you could do. If you just have one set of parentheses, and in particular it looks like if I distribute, it might be kind of messy. Sometimes it is actually just nicer to get rid of that multiplication. So in order to get rid of that multiplication, I would undo first dividing by 3 by multiplying both sides by 3. 3 divided by 3 cancels out to make 1. I'm left with 3x is equal to 1 times y minus 5. Just for illustration purposes, I would then say you would either distribute multiplying by the 1 or divide by 1 on both sides. Either way, 1 doesn't actually do anything in terms of multiplication or division. It just keeps everything the same. But you could sort of think I'm dividing by 1 really. And then you have 3x is equal to y minus 5. And as your last step, you'll want to undo subtracting 5 by adding 5 to both sides. So then I have 3x plus 5 is equal to y. And then you might want to remind yourself you actually just found the inverse function, so I can use that inverse function notation. And then you might just want to kind of ask yourself, does that actually kind of make sense intuitively, that if originally I do multiplying by a third, then subtract 5? Well, actually, sorry, I just reversed that order. Parentheses first, of course. If first I subtract 5 and then I multiply by a third, on my inverse, I multiply by 3, then add 5. So these feel like kind of opposites. I not only did sort of the opposite order, first I subtract 5, then multiply by a third. Here, I first multiply by 3, the reciprocal of a third, and then I add 5, kind of undoing the subtracting 5. It feels like an inverse. Go ahead and try the next one yourself, and then we'll go over it. So I have just that optional first step of first replacing f of x with y. Then we get into the real first step of that you have to flip x and y to start orienting that you're finding an inverse. So x is equal to 6y plus 7. Then you want to actually solve for y. So in this case, I want to undo adding 7 by subtracting 7. So then I get x minus 7 is equal to 6y. And then I want to undo multiplying by 6 by dividing by 6. So y is equal to x minus 7 over 6. An equivalent way you could write this is that dividing by 6 is the same thing as multiplying the whole thing by 1/6, so it's sort of similar to the other one. You don't have to rewrite it that way. This way is a totally fine way to keep it. Keep in mind when I have a big old fraction bar like that, there are secret parentheses on top of that numerator saying you have to do what's in the numerator first. So we have our inverse function is equal to 1/6 times x minus 7 in parentheses. Or you could have written that as x minus 7 all over 6. Either way. And again, kind of as a sanity check, they feel like they should be inverses. If on the original you first multiply by 6 then add 7, on the inverse you're first subtracting 7 and then multiplying by 1/6. Oh, and of course it said in the directions to find domain and range as well. I just was on automatic pilot here. So for both of these guys, if I have a linear function and a linear function, what's the domain on those? It's just negative infinity to infinity. So here for this inverse function, he's linear. It's negative infinity to infinity for the domain. And his range is the domain of the original, which is also linear, which is negative infinity to infinity. Same deal here. The inverse is linear, so his domain is negative infinity to infinity. And for the range, that's the domain of the original, which is also negative infinity to infinity. Some of these might require slightly more work to think about the domain and range, but let's get into them. So for this first one, we want to, again, first do our optional first step of rewriting f of x as y. Then we want to do our real first step of flipping x and y. So we'd have x is equal to the cube root of y plus 5. Then we want to actually start solving for y. So here, since everybody's underneath the cube root, the first thing I want to do is undo the cube root. And the opposite of cube rooting is cubing. So then I have x cubed is equal to y plus 5. And as a last step, I then want to subtract 5. So then I get x cubed minus 5 is equal to y. And what I just found was the inverse function. And again, it should actually feel like an inverse. Because here, if I first add 5, then I cube root it, now I'm cube rooting and then subtracting 5. I'm undoing it. And I could formally check that it's an inverse by plugging this in, and it should just output x. Now I want to check my domain and range. So for my domain, for this inverse, this is a cubic function. I'm allowed to actually plug anything into it. I only have to worry about square roots and that sort of thing. For something like x cubed, its domain is just negative infinity to infinity. For its range, you want to look at the domain of the original. And on the original, his domain is actually also negative infinity to infinity. You might be going, wait, there's a root. I've got to set that greater than or equal to 0. That's only true for even-powered roots. For cubes, you're fine. For example, the cube root of negative 8 is just negative 2. Because a negative 2 times a negative 2 gets you a positive 4 times another negative 2 gives you negative 8. So you are allowed to plug negatives underneath cube roots. And because the domain of the original is negative infinity to infinity, the range of the inverse is negative infinity to infinity. For this last one, we want to do the same sort of process. So first, I'm going to do sort of my optional first step of just rewriting it as f of x as y instead. Then I actually want to flip x and y. So I get x is equal to 1 over y. And now I want to solve for y. And there's a couple different ways you're going to do this. You could do this. I'm going to do it just kind of the most intuitive way in my opinion. So I first want to undo division with multiplication because I don't want y's hanging out there in a denominator. Now I have x times y is equal to 1. Keep in mind that y times x is the same thing as x times y. That's like saying 2 times 3 is the same thing as 3 times 2. Then I want to undo multiplying by x. And how do I undo multiplying by anything? I just divide. So I could actually divide by x. And actually, this is a case of a function whose inverse is the same as the original. Very rare that that happens, but this does happen to be an example where that's the case. So for the domain of this function, well, what's the one number x is not allowed to equal? Can't equal 0, because that would make that denominator 0. So its domain is negative infinity to 0, union 0 to infinity. For the range, that might be originally kind of hard to think through, but remember the range is going to be the domain of the original. In this case, 1 over x. And on that original, what can x still not equal? 0. So here, that's why the range is negative infinity to 0, 0 to infinity. Fancy way of saying every single number except for 0, parentheses of that 0 saying to skip over it. For these types of functions, the reason why we have to restrict the domain is because this square root function has a restriction on the domain. In particular, if I just asked you for the domain of this original, the way you would even solve it without me telling you would be that you would have to know that x plus minus 5 has to be bigger than or equal to 0. Add 5 to both sides in order to undo subtracting 5, so x has to be bigger than or equal to 5. Because now this is an even-powered root, so you have to make sure whatever you're plugging in stays strictly positive. So now let's think through the domain and range on this guy. So let's first do our optional first step, which I think, what color was I using for that optional first step? I was using blue, so let's continue using blue. So for that optional first step, this function, f of x, I can go ahead and replace with y, is equal to the square root of x minus 5 with a plus 3 hanging out on the outside. Then I want to do my required first step of switching x and y. And now I want to solve for y. So here, because that plus 3 is hanging out on the outside, I first want to undo adding 3. So I'm going to subtract 3 on both sides. 3 minus 3 gets me 0. I'm left with x minus 3 is equal to the square root of y minus 5. Then I want to undo this square root by squaring both sides. And when I square both sides, I need to use parentheses and then square. That cancels out to make just the original thing underneath the root. So then I have x minus 3 all squared is equal to y minus 5. Now as my final step, I want to undo subtracting 5 by adding 5 to both sides. So then my inverse function is equal to x minus 3 all squared plus 5, which this is actually a quadratic function in vertex form. That's something we'll be going over more later. Now let's think about the domain and range on this guy. So for the domain of this function, originally you may think, oh, well, I am allowed to plug in anything, which is true for the function by itself, but keep in mind there was a restriction on the domain in the original. So if we're thinking about that restriction on the domain in the original, this actually will inform what our domain and range look like for this one. Because on the original, they gave us that the domain was 5 to infinity. And let's actually think about what that means for its range. Because if I plugged in 5 exactly, the square root of 5 minus 5, well, 5 minus 5 makes 0, and I'm left with 3. Is there any way that this function will possibly get smaller than 3? There is not. Because whatever I plug into this square root, he's going to just keep on getting more and more positive. So on the original, they gave us that the domain was 5 to infinity, and we could figure out that the range must have been 3 to infinity, because if I plugged in the smallest value on the domain, and then I noticed it just started at 3 and then kept getting bigger from there, it must be going from 3 to infinity. For the inverse, that means I have to flip that. So the range of the original, 3 to the infinity, becomes the domain on the inverse. Not because I can't plug in smaller numbers to this function by itself, but because this domain has to then become the range on this, which will then impact that domain on the inverse function. So for problems like this where they give you an original restriction on the domain on the inverse function, it's actually going to be most helpful to figure out the domain and the range of the original, and then know that on the inverse that means you have to flip them. This is another great example of where they've done this, and they've done this intentionally because in order to make it one-to-one. So here they tell you a restriction on the domain, which gives you then also a restriction on the range. So let's sort of think that through. There's also, for this particular function, a different way you can figure out the range, but we haven't technically gotten to it in this class. So let's stick with methods that we have so far in our toolbox, although if you're rewatching this video at the end of the semester, you'll have other things in your toolbox. So on the original here, its domain is -3 to infinity, and let's see if we can figure out its range. So if I plug in -3, that becomes 0 squared. And as I plug in bit numbers bigger than -3, will this always be getting bigger, or is it even physically possible for it to get smaller? It's always going to be getting bigger because I'm taking numbers that are bigger than 0 in absolute value and I'm squaring them. So they're just always going to, but as soon as I square them, it becomes positive. So for its range, its lowest bound is 0 when I plug in -3, and then it keeps on getting bigger. So even before I've even figured out the inverse, I would argue you could go ahead and write the domain and range of the inverse. What must it be? The domain has to be 0 to infinity, and the range has to be -3 to infinity. We already know that to be the case, but we still also have to find the inverse function. So let's do that. So if f of x is equal to x plus 3 all squared, and I apologize that my Steam for some reason seems to be like popping up in the corner. I don't know if you can see that. If you can, sorry for that distraction. If you can't, sorry for that little segue in the side. All right, let's keep going though. F of x is equal to x plus 3 all squared. As an optional first step, I would go ahead and orient myself that f of x is equal to y. Then as a real first step, you need to flip x and y. So then this becomes x is equal to y plus 3 all squared. Now I actually want to start solving for y. So first I want to undo a square. How do I undo a square? I square root. And you might be saying, oh, I have to plus or minus the square root, but you don't in this case. And the reason why you don't in this case is because I've restricted my domain and I am explicitly finding a single function. So I am just going with only the positive square root. If you're solving like quadratic equations, and a lot of times normally whenever you're undoing a square with a square root, you need that plus minus. Because I've restricted this domain in the first place, I no longer need that plus minus. So then I just have regular old square root of x is equal to y plus 3. As the last step, I want to undo adding 3 by subtracting 3 on both sides. So then the square root of x minus 3 on the outside is equal to y. So I just figured out the inverse function. And that should track with what I predicted my domain of the inverse to be, 0 to infinity. That is indeed what I'm allowed to plug in for x in this case. And for that range similarly, if I plugged in 0 for x, -3 would be the smallest y value, and that would only keep on getting bigger. So both of those also make sense with what I just found to be the inverse function. As always, please be sure to take a look at your textbook for even more examples and ask your instructor if you have any questions. And happy mathing!